So this is the version 3 of the brain tumor classification. In this exercise, I use a already pre-trained model, which is Inception V3 made by Google, and then I extracted a feature from the model, and then after that I fine-tuned the after result uh, for this specific purpose of classifying brain tumor. So I import modules, create data frame, which I really just copy from the other guy. And we split the data as usual. And here I'm downloading the Inception V3's weight. Inception V3, like I think you can like classify like 500 different um, classes, like horse, carrots, apples, and so on. But so the so it could be generalized for many different images as long as you use the main part of it and not the extreme end, the top result. So here um, we have this local wave file of Inception V3, so same input shape as usual. So yeah, as I said, we're not including the top, so we're not loading the classification layer at the top, so that we can have the generalized uh, intermediate um, stuff. It's important to set the pre-trained models as a non-trainable, because if you're trying to train this entire models, it's not going to work it's not going to work well, and it's already trained by these professional Google people, and it's probably not going to get any better. Here we're using the layer mix 7, uh, which is not the classification layer at the top, um, and these are pretty much the same. After that, after this, Google's Inception V3's pre-trained model uses the flattened layer, dense layer, and some dropout, and we have this um, final layer for classification. Here we're using Atom for the optimizer, with a really small learning rate, because it's already trained pretty well, so we don't need a huge learning rate. We just need to fine tune it a bit. And then, as we have already done so, we have this data pre-processing with the image data generator, and we can train it. We have the result, so we can look at this a pre-trained version. So this yellow and green, and as you see the validation, um, it starts from like 97% already, and then it pretty much stays the same at 97 to 98% accuracy really soon, which just goes to show the effectiveness of using a pre-trained model or feature extraction. So after that, we're gonna fine tune it. So we should only fine tune it after we train the top level classifier, and we're only fine tuning the top layers of the pre-trained model only. So first of all, how we fine tune it is we set the top layers of pre-trained models as trainable. So we're on for all after mixed 6, and then we just need to recompile the model. So we set this optimizer as stochastic gradient descent, and here again we're employing really small learning rate. As the name implies, after all, it's a fine tuning, not extreme makeover tuning. And once you train that, it was supposed to give you a slightly better result, but there's not significant improvement with inaccuracy and fine tuning, but it shows a more smooth curve and consistency. So I guess in a way it's more of an improvement. I don't really know why it didn't show much more improvement. I guess one reason could be that it's already reached a high enough accuracy that it's hard to improve more just with fine tuning. But yeah, so that was the version 3 with feature extraction and fine tuning.